All right. Our last week together. I'll admit, I'm still debating on what I want to do with our last week in terms of homework. And I'll admit, there's a part of me that says I just might not do any. Just because, like I said, we've covered everything, in my opinion, that I wanted to cover in steel design. So this is just sort of the cherries on top. What I want to do today and Wednesday is discuss lateral loading. And I want to discuss wind and earthquakes. That's what I want to discuss. If I give you a homework, it would probably be a combined one, but I'm not, I haven't fully decided if I'm going to do that or not, and there's a chance I don't. If I assign it, it'll be Wednesday, and it'll be a really short one. But I'll keep you posted. Let me just jump right into it. Does everybody have the QR code? Okay. All right. So I also think today may be a somewhat short day. I don't think we'll be here the full 50 minutes because I was thinking, do I try and do wind and earthquakes in one day? I think that would be too much, but separated we might have a little bit of extra time, but that'll be all right. Okay, so let's talk about wind first. But just to give you kind of an idea, we're going to be focusing on wind design and we're going to be focusing on earthquake or wind loads and earthquake loads. Now we've talked about this before, but the idea in building design is that you do not design the entire building to withstand wind forces. You install a certain subsystem inside that building to withstand wind forces or earthquake forces. Just like the idea behind a vehicle, you don't design the entire vehicle to hold back, or even the entire car seat to hold back a passenger in the event of a collision. You have a subsystem installed specifically for that. And we call that subsystem a seatbelt. Okay, the whole car isn't holding you back, or the whole seat isn't holding you back. It's a subsystem of those components. And so in building design, we're talking about bracing systems. So we're talking about either brace frames or moment frames or what have you as loads hit the building laterally. Okay, so what we're talking about are wind loads today. Okay, so wind is one of the two main lateral force events that buildings would see. I guess I'm sort of ignoring a third one, which is earth pressures. So if you had a part of a building that was underground, or there was some sort of retaining wall type element, then that's going to be subjected to lateral earth pressures and whatnot. But I'm sort of talking about loads above the ground, as it were, wind being one and earthquakes being the other. Wind is, in my opinion, where structural engineering really starts to get a little challenging. To put things in perspective, if I were designing the second story floor beams in this building versus designing the fourth story floor beams, the floor beams that are subjected to gravity loads aren't really going to behave any differently on this story than they are the story above us. They're pretty much going to be the same beam, for lack of a better term. In other words, if you have a building, let's say, that has repetitive floors and under gravity forces, you have the same span, the same loads, the same bracing configurations, it's going to be the same thing. Okay, that's not the case with wind loading. Wind is one of those things that varies as a function of height, and the taller a building gets, the bigger, I should say, your wind forces are. Is there anybody here that's ever been? The example I like to use is if you've ever been on top of the Empire State Building or the observation deck on the Empire State. If you ever go up there, it's really windy. The higher a building gets, the larger the wind forces are. In fact, it's kind of parabolic in nature. We're only going to give a very cursory review of wind forces, but a couple things to keep in mind is that not only, so for example, if you have a building and wind strikes the building in one direction, you not only generate forces along that face, the windward face, but you'll generate forces along all of the other faces as well. So for example, just some terminology for you, if this is the windward face, we would call this the leeward face. And so that face of the building is going to see an aerodynamic effect as well. Now, Dr. Waite would be proud of this. What we're going to do is we're going to go through the base wind speed equation. And where it comes from is Bernoulli's equation, okay? So what I want to do is I want to consider some sort of building that's being hit by wind, and we're going to treat wind like it's a fluid, okay? So I'm going to sort of consider 2 points on my schematic. I'm going to consider point A, where the wind is flowing, and point B, the stagnation point, where it's hitting the building, okay? And if I think about this from a Bernoulli's equation perspective, at point A, I'm going to have wind moving at a given velocity, but there's really no pressure because the pressure doesn't arise until you hit point B. At point B, we're going to have some sort of pressure, but we're not going to have any velocity, right? And so the idea is that if I give you a wind speed, if I give you wind hitting a building at a certain miles per hour, okay, could you tell me how much pressure that's applying to the building? Does that make sense? That's kind of the idea. And if you think about wind, I mean, how do you characterize wind? I mean, if I go on my iPhone right now and I look up the weather, you know, for the given area, and I look up the wind, it's going to tell me the wind in miles per hour, right? So ultimately what I'd like to be able to do is to take that wind speed and so many miles per hour and convert it to a pressure that's going to be applied to the building for the purposes of design. And this is really a Bernoulli's equation problem, at least fundamentally, okay? Now, I'm also going to say that for the purposes of this discussion, I'm going to consider point A and point B at equal elevations, and we're going to adjust the elevation parameter later, okay? So just keep that in mind. Okay, so if that's the case, what we're going to do is we're going to start with this, right? This should be familiar, hopefully, to everybody in this room. Anybody not familiar with this? I'm sure Dr. Waite would just, you know, give you the professor look if you didn't know what this was. So here's our Bernoulli's expression, okay? And so usually with a Bernoulli's equation problem, the first thing that we'd like to do is to start to cancel things that aren't really relevant for our problem. So for example, we're going to cancel the elevations because we're going to assume they are at equal elevations. For point A, we're going to cancel the pressure. And for point B, we'll cancel the velocity, okay? So we'll arrive at this, okay? So this is what we'll arrive at, and then we'll take this and we'll rearrange it, and we'll solve for the pressure, and we'll get that the pressure at point B is going to equal the velocity squared times this quantity gamma over 2g. Now, by the way, what is gamma? The unit weight of what? What's that? The unit weight of air, the fluid, right? In this case, it's the unit weight of air, okay? So the unit weight of air is something that you would look up. So if you look that up, you would get that the unit weight of air is something like 0.0765 pounds per cubic foot. And that's the unit weight at sea level, okay? So how do we go from this to this expression right here? Well, just a little bit here on the board. So ultimately what I would like to do is I'd like to be able to plug in a velocity in miles per hour and get out a pressure in pounds per square foot. So we have gamma over 2g times the velocity squared. So I've got 1/2, that's the 1 over 2, that's the 2 right there. Gamma is this, and g, that's 32.2 feet per second squared in US units, right? So what I've done from this line to this line is I've taken all the numbers, stuck the numbers out here, and then what do I have for units? Well, what I have for units is I have pounds over cubic feet divided by this, so times second squared over feet, right? So flip and multiply, and I get this factor here, or this unit here. This is complicated, this is confusing, okay? So maybe what I'll do is I'll simplify this a little bit. And then here, instead of 2 times 32.2, maybe we'll make that 64.4, just so I don't have to keep writing that. What I'm going to do for this is I'm going to rewrite this as pounds per foot squared times second squared per feet squared. Is that a fair way of doing that? Okay. And then what I'm going to try and do is I'm going to try and get rid of this term right here. I'm going to try and get rid of that. This marker is dead. I'm going to try and get rid of this. But more specifically, I'm going to try and get rid of it by recognizing my goal is miles per hour. Okay. So if I look at seconds, what do I know? I know that there's 3,600 seconds in 1 hour, right? Okay. but I need to square that because this is second squared. So that's going to go away right here. And then for feet squared, I know that there's 5280 feet in 1 mile, but I need to square that as well, right? And then this will leave me my velocity in mph. So if you take your Casio FX115 ES Plus or similar calculator, and you say, okay, 0.0765 divided by 64.4 times 5280 squared over 3600 squared, you get that value right there. So whenever you look up the base wind speed equation in ASCE7, and it looks like this, okay, so the base wind pressure equation is this random number right here times these constants times v squared. What is this? It's Bernoulli's equation. That's really all it is. This is Bernoulli's equation with a series of adjustment factors on there. Okay. So how do you calculate the pressure on a building for a given wind speed? Well, we would take that wind speed in miles per hour, multiply it by 0.0256 times that base wind speed squared, times a few corrections. Okay, what are the corrections? We have 3 correction factors that we're going to apply, but most of them we're not really going to worry about, so I'll sort of work my way around. We have a wind directionality factor that accounts for the wind potentially striking the weakest side of the building, but this is essentially a lookup, but for most routine buildings, that value is 0.85. This term KZT is what's called a topographic factor. So the idea behind KZT is if you had a building that was, let's say, on top of a hill that had a really sudden slope, that as the wind hit that slope, you would get a certain wind speed up effect on the building, and that could affect the wind pressures on the building. But for most routine design, especially in a city like Huntington and whatnot, it would be 1, since Huntington's pretty flat. KZ is the term that requires a little bit of work, because what this does is it adjusts your wind speed pressure as a function of height. So as the building gets taller and taller and taller, your KZ value is going to increase and increase, and ultimately your wind pressure is going to increase as well. Now your base wind speed is a lookup. That's a function, by the way, of your risk category. Remember we talked about last time how there were 4 risk categories that affect how the building is classified in regards to environmental loads. So remember, risk category 4, that's your buildings that if they were to collapse would affect everybody in the city. So things like the hospital, the fire station, 911 call centers, police, anything where the loss of those services would affect everybody in the community. Whereas risk category 1 are sort of unmanned facilities where if they were to collapse really wouldn't affect anything globally, like a grain silo, an unmanned warehouse, things like that. Yeah, it would suck, but it certainly doesn't have as much impact as the collapse of a 911 call center or whatnot. Remember, risk category 3, those are buildings with a large population of people that would need assistance in getting out. So things like a theater, a music hall, a stadium, an elementary school, assisted care living facilities, things like that would be risk category 3. Risk category 2 is pretty much everything else. So this building would essentially be a risk category 2. Yeah, it's a school, but it's not like an elementary school where like kids would need assistance getting out. It doesn't really work like that. Now, like I said, this is a lookup, and it's based on your risk category. This is sort of a general schematic as to what your wind speed maps look like. Again, we're going to use that hazard tool that I showed you last time. We're going to use that today. You'll note that what this wind map is showing is essentially you're controlling wind events, you're controlling climatological events that would affect what wind speed you're going to use for the purposes of design. And for the most part in the country, thunderstorms are really the event that governs where your wind speed is coming from, except for coastal regions because of hurricanes. Okay, along coastal regions, the wind speeds are going to be higher. Now there is one thing though that you might be thinking, well, aren't you forgetting a windy event that happens in this area of the country? What wind event am I talking about right here? Tornadoes. We're forgetting about tornadoes. Tornadoes are a little bit of a specialty design inside structural engineering. So like the idea behind a tornado design is, so let's say you're designing a building, you might design the building for regular old, wind loads, but there is a certain portion of the building that you design for increased loads, and that's your tornado shelter if something goes wrong, if you have a major tornado event. If you've ever been in a tornado-prone region, especially in public buildings, you'll notice that there's like the main area of the building, but then they'll say, in case of a tornado, go here. So everybody know what I'm talking about? So those areas of the building have been designed for increased wind loads as a result. So just throwing that out there. So that's a little bit more of a specialty design. Okay. All right. So like I said, as buildings get taller, wind speeds increase, wind pressures increase, I should say. And then we account for this by using what's called a exposure coefficient. And so this is the term KZ. So it's a function of the height of the story. And so I'll show you how this expression works here in a little bit. But basically what happens is that you can, this is your exposure coefficient term. For anything that's less than 15 feet, we pretty much assume a constant wind pressure. But as we get higher than 15 feet off the ground, we start varying the wind pressure as a function of height. And so it's a function of what's called this gradient height and what's called an exposure constant. And so the exposure constant, we talked about this a little bit last time, how dependent upon the exposure of a building, we can get different collections of snow on the roof. Well, it's the same thing here where we can get different exposures of wind pressures on a building. If we were designing buildings in Huntington, like in the city proper, we would probably use a category B. And then as we get sort of more towards Ona, maybe we're talking about category C. If we get towards the Outer Banks, we're looking at category D. Okay, so category B is what you would find in most urban, suburban settings. And I would say if you're doing a lot of like mid to high rise structural steel design, you're probably going to be operating in category B because you're probably going to be doing that construction in a urban, suburban environment. One of the things that is kind of funny is that there's a category B, C, and D, but there isn't a category A. But category A is sort of a section in the spec that's reserved for wind tunnel testing. And so if your building got like pretty tall or pretty complicated, you'd probably end up just, in lieu of doing a bunch of calcs to figure out your wind pressures and whatnot, you'd probably just take a scale model, put it in a wind tunnel, and just record whatever pressures you get, and just use those scaled up for the purposes of design. Which is a little bit of a pricey endeavor, but that makes sense if your building is pretty challenging geometrically or pretty tall, if that makes any sense. Sound good? Okay, so just to give you kind of an idea on how wind pressures would work, I've got this model here. This is essentially like honestly kind of reflective of the building that we're in now in terms of height and geometry. Now I have purposefully used some slightly different story heights and whatnot here, mainly because I just want you to see where the numbers are coming from. If I'm being honest, that might be a little bit unrealistic. Not to say it wouldn't happen, but most buildings are going to have pretty even story progressions from story to story to story until you get maybe to the roof or maybe down here. So maybe the first story is a little bit taller than everything else. Maybe the story from the last story to the roof is a little bit taller. We're going to determine base wind pressures at each story, okay? And we're going to do that for this frame shown. So we're going to assume that this is a commercial office building in Huntington, West Virginia. So if it's a commercial office building, we're going to assume it's risk category 2. And since it's in Huntington, we're going to assume it's exposure category B, okay? We're going to take the KZT term to equal 1 because we're going to assume it's pretty much on flat environment. We don't really need to worry about that. And we're going to try and determine what are the pressures at each height of the building. So that's what we're going to sort of work on here. So let's see what we can figure out. Okay. Okay. So the first thing that we need to do is we need to figure out what our wind speed is, our base wind speed for this area. And so if you recall, we can go to hazardtool.org to figure that out. So I have a browser open right here. So this is our hazard tool. And we're just going to put in Huntington, West Virginia and see what we can get. Okay, so here's Huntington, West Virginia. That should look pretty familiar, hopefully. Let's see. So let's look at our risk category. So we're going to assume risk category 2. One of the things you'll notice is that it's asking for a site soil classification. That doesn't affect really anything that we're doing yet, but it does affect your seismic forces. Okay, because dependent upon the soil characteristics, you can get different accelerations that are transferred to the building that generate seismic forces that you need to design for. All right, next thing we need to do, we do need to select the spec, although we're just going to use the standard one. If you're going off of an older spec, just so you're aware right here. So this is, we're operating off of ASCE 7. And so where it says 7-10, 7-16, 7-22, those are the years that they came out. This is 2010, 2016, 2022. So we're going to operate off of the newest version of ASCE 7. And we're going to just calculate a wind load and see what it tells us. Okay. So what it's saying is that the wind speed is 107 miles per hour. And you could get some more details if you want on mean recurrence intervals and things like that. But we're going to use 107 miles per hour for our design. Okay, we're not in a hurricane-prone region as defined by ASCE 7. We don't really need to worry about that. So that's going to be our base wind speed. Okay, so 107. I gotta say, ASCE really has this hazard tool really is kind of nice because you ended up having to use these really confusing maps sometimes to look up environmental loads, particularly snow loads. I always found it kind of challenging to make sure I was in the right region, whereas this is sort of doing a lot of the work for you, and it's really kind of nice. Okay, so excuse me. Let me get rid of my keyboard here just for a quick second. All right, so okay. One thing I will say about this number, this wind speed of 107 miles per hour. Let me see what happens. Let me pull back up my. Let me pull this up here. Okay, I'm going to go back to this. I'm going to change it to an older version of the spec and see what we get. Okay. I was curious if they had how much that had changed a little bit. It had changed a little bit. So they do change the wind speeds a little bit from spec to spec. That's one of the reasons that you buy these specs every 6 years is because they collect weather data every so often. So you can see the wind speed went from 115 to 107. So they're always sort of tweaking it a little bit based off of the most current weather data. I just want to see how much it was different. Okay, so we're going to use a wind speed of 107 miles per hour. We're within exposure category B, okay? So in exposure category B, what that does is that affects these terms here, this term ZG and alpha. So you have different values for each category. Just to give you kind of an idea of what these are, alpha is sort of a reflection of how much your wind speed changes as a function of height. So like as your building gets more and more exposed, you have different degrees of pressure changes across the height of the building. And then this term ZG is what we call a gradient height. And essentially what that means is once you get past this height, you can stop worrying, bless you, you can stop worrying about the wind speed changing as a function of height. So, but I mean, we never really get to this point in practical design when we'd have to design a building that's 3,000 feet tall. And at that point, we'd probably abandon all this and do some sort of wind tunnel testing anyways. But right now, we're just using it as a parameter for calculating our wind pressures as a function of height. So we're going to have an alpha of 7.5, and a gradient height of 3280. And these come from category B. I guess what I should put here is this is Huntington and risk category 2. Okay. All right. Everybody with me so far? Okay. We are going to take, I'll put a note here. We are going to take KZT equal to 1.0, and we're going to take KD equal to 0.85. Okay. Okay. All right, so just to sort of illustrate how this is going to work, I'm going to do one of these by hand, then I'm going to do the rest of these in Excel, okay? And the way that I'm going to do this is I'm going to look at my elevations for the building. Now, whenever you look at these elevations are elevations from ground level, okay? So, for example, here I'm going to say the elevation is 0, and here I'm going to say the elevation is 12 feet, okay? What's the elevation of the third story? So if I'm here, how far up am I off the ground when I'm here?
26 feet.
26 feet. Okay, there we go. So you can kind of see the pattern here. Okay. Here, 26 plus 15 is 41. And this is 53 feet, right? Okay. So somebody pick like one of these 4 stories. I really don't care which, but maybe something on the upper end.
Top.
The top. Okay, we'll pick the top. All right. Okay, let's consider z equals 53 feet. Okay, so this is my expression for kz. I wrote it up here on the board so that I wouldn't have to keep, writing it down. By the way, there's a third row. The third row just says that the value is 2.41, and that's if you get above your gradient height. But our gradient height is 3,000 feet. So I'll be honest, I kind of didn't even bother writing it because, again, most structural engineers really aren't designing buildings that tall. Okay, so what we're going to do is we're going to calculate our KZ term. So which expression are we going to use? Are we going to use the upper expression or the lower expression?
Lower.
Lower, right? Because so what this is saying right here, so remember wind speed or wind pressures vary as a function of height. But if your building height or your floor height is less than 15 feet high, we're just going to use a constant pressure. Anything past 15 feet, the pressures are going to start increasing as a function of height. So what we've got here is that our KZ term is 2.41 times Z over ZG, and then it's raised. So I wrote it like this here on the screen because this is a 2, not a Z. I really tried to be cognizant to say that anytime there's a Z, I stuck a line through it. Anytime there was a 2, I didn't, because I know my 2's and my Z's kind of look similar. So just to make sure it was crystal clear, I wrote that as 2.0. So this is going to be 2.41 times 53 feet over 3280 feet. And this is 2 over alpha, and our alpha is 7.5. Okay, and so what do we get for this? We'll say like 3 decimal places.
802.
Sound good? That's what I got. So therefore, our pressure at that height, so our wind pressure at that height, is going to equal this. So that's 1. That's 0.85. And that's that. And what do we get for this? $19.98 pounds per square foot. That's pretty easy, right? So this is how you would do calculate wind pressure as a function of height. Now we've got multiple heights for this building, and so I tend to think that the easiest way to handle that is Excel. So just to run through a quick Excel calculation. Whoop, what happened? We lost my screen. Let's try this. There we go. I say I lost my screen there for a second because I snapped my keyboard back. Okay, so I tend to think that the easiest way of handling this is to just do this as a quick Excel calc. So I can do this pretty quickly. I'll show you how I would handle this. So I would say, okay. So we have our levels, and then we have the roof, the 4th floor, 3rd floor, 2nd floor. We have our elevations. And so what did we have? We had 53, 41, 26, and 12. Is that what we had, right? And then we had, okay, so let's look at our, let's write down our environmental, our relevant data. I'm just going to stick this in a column here since this is small enough that it's not that big of a deal. Let's see, this is 7.5. And then okay. All right, so our KZ term, here's how I'm going to compute it. So I'm a big fan of being lazy when it comes to doing Excel, and I'm a big fan of keeping this as simple as possible. So let's just sort of take a look at the expression real quick. So the expression, like when I look at this, the first thing I think of is an if statement, right? So I'm thinking, if this is true, then this, otherwise that. But let's take a look at the formulas, okay? What's happening between this formula and this formula? The only thing that's changing is this numerator right here, right? And so what this is saying is that if z is less than or equal to 15 feet, just use this. But if it's bigger than 15 feet, replace that with z, right? So really what we need to do is, like this is the way I would do it, is just say equals 2.41 times, then I'm going to have a term raised to the 2 over alpha, okay? All right, and inside here is going to be a fraction. The denominator is going to be that. So what goes on the numerator? Well, it's either 15 feet or z. Really all we're after is what's the maximum? And then if we keep going, That's what we've got. And what's happening here is it doesn't matter if it's 12 feet, 13 feet, 14 feet, etc. It's just using the constant value of 15, which is exactly what we're supposed to be doing. Okay, so KZT was 1, KD 0.85. And then to calculate our pressure, so that squared. Did I do that too fast, or is everybody kind of like good with that? I'm hoping that's pretty straightforward. So I'm hoping that the calculation is pretty straightforward. Now, a big question might be, well, okay, Dr. Mike, what am I supposed to do with that? The way I would handle that is this. So if I was in the process of performing some structural analysis, what did we have? Z equals 12 feet. $41 feet. So here's my here's my building, right? And so essentially what I've calculated are pressure loads. This one is 19.98. This one is that. This one is that. And that one is that. So we would just apply them essentially as pressure loads, right? And so the idea is, okay, imagine, let's look at it three-dimensionally. So here's my building, right? Okay, and I don't know, let's make up a number. Let's say that the building has a length of 120 feet this way. I'm just making that up, right? So we would say that, I don't know, maybe there's a brace frame on this side of the building, a brace frame on that side of the building. Half the load goes here, half the load goes there, apply tributary width, start analyzing accordingly. So, does that make sense? Again, like, I think that the hard part is sort of getting here. Once you get here, it's just statics. So, sound good? Okay, I do want to mention a couple things before we call it for today. So the first thing I'll mention is I gave a very high-level overview of wind, and there's a lot of things that I'm not talking about. I'll go through a couple of them right now. So the first thing that I'm not talking about is gusts and changes in internal versus external pressure. How many of you have ever been in a building like this and it's been a really windy day and you found that the doors have a tendency to want to stay open? Have you ever seen that? So whenever wind hits a building, what happens is not only do you generate pressures outside the building, but you generate pressures inside the building as well. So that pressure that we just calculated, you would ultimately then adjust that for not only gust effects, but changes in internal versus external pressure. And basically the way it works is, the way I've always done it is you have a big old spreadsheet and you have, case 1, case 2, case 3 versus positive pressure, internal pressure, and so on and so forth. And you just take your controlling one for the purposes of design. The second case is one that I find, at least as an engineer, to be the one that's the most interesting. And this is what happens when there's wind eccentricity. So the problem that I put here on the board was essentially a building that's just a big old rectangle. And I got to be honest with you, engineers love buildings that are just big old rectangles. Architects hate them because they look horrible, but that's why I'm an engineer. Let me show you one of the challenges that can happen when your building footprint looks a little wonky, which in all honesty is not that uncommon, okay? So let's deal with a pretty simple floor plan, okay? Let's deal with like an L-shaped floor plan. Let's look at a building that looks like this. Okay, so like the idea is you have a column here, a column here, column here, column here, column here, column here, maybe a column there, maybe a column there, right? So, you know, we're looking at this from the elevator looking down, and so that's what the building looks like, okay? So, let's say, for the sake of discussion, that wind hits the building, and let's say that wind is hitting the building this way. Okay? So, how are you going to resist those wind forces? Well, you're going to need some sort of bracing system. Remember those like diagonal braces that we talked about that go from column to column? So you're going to need some sort of diagonal bracing system. Let's say, for the sake of discussion, that you put your diagonal bracing like right here and right here. That makes sense, right? I mean, like if you're trying, like it really wouldn't make sense to put bracing only on one side. Maybe you'd put them in both sides so that, you know, half the wind force goes to this frame, half the wind force goes to this frame, so that they're sort of equally resisting that wind load. Does that make sense? So if I were to treat this frame as an element and this braced frame as an element, would you agree that maybe that point right there is the center or the centroid of these two frames? So I'm going to call this I'll call that the center of rigidity. In other words, as wind hits the building, you can sort of idealize all the wind forces point is hitting that point right there. Okay? Now I want you to ignore the frames and I want you to look only at the floor system. So I've got this floor system, maybe a better way of doing it, maybe I'll fix this a little bit, make it a little bit more even. Okay, that's a little better. Okay, so this point right here is the center of rigidity of the floor system, or the bracing system. Where's the center of rigidity, or the center of mass of this floor slab? You know, this is an angle. Maybe it's like right there. So now there's a difference. Actually, let's make it a little bit more extreme. Let's put it right there. Let's call this the center of mass. Okay. Let me ask the question a little more generally. Do you agree that it is possible in building construction that the center of mass of the floor slab and the center of rigidity of the bracing systems are not in the same place? Does that make sense? So what that means is that if the center of mass is here and the center of rigidity is here and wind strikes the building, the whole building is going to want to twist under wind load. Why not? Wouldn't that happen? So the short answer is yes, that could happen. Okay, so that's where things get kind of interesting. Whenever the center of mass and the center of rigidity are in a different spot. Like, so the way the spec handles that is they make you assess various different load cases, and some of those load cases involve, like, for example, we'll take the wind load, and fully apply it to this space, fully apply it to this space, or fully apply it this way. But then what we might do is we might say, okay, let's apply some of the wind force this way, but let's also add a twisting moment to the building as a whole. And so we'll take whichever one of these worst case scenarios results in the worst case forces on our bracing system, and that's what we'll design for. So that's when things really get fun. So that's one of those like steel design 2 problems. Like if we had a second steel design course, I'll talk all about this. Talk about this and eccentric connections and all sorts of stuff. So one of these days, I wish I had more time to teach this stuff. I just don't. So dang it. I'd love to talk about this stuff more though. But alas, I only have 5 minutes. So any questions on this? I'm going to let you go 5 minutes early. I'm going to pull up the QR code one more time. We'll talk about earthquakes next time, and that'll close it out for the semester. We'll do our exam review on Friday. So, but that's all I've got.